Hello calculus students and general seekers of truth. Welcome to the second video in our series on polynomial and Taylor series. And in the last video we talked about how to do linear approximation, and in this one let's discuss the pros and cons of linear approximation, and then we can talk about why we need a better method. Okay, so one of the good things about the linear approximation is that it's quick to calculate, and that it is accurate near the special point. Okay, and if you don't know what I mean when I talk about special point, look at the last video. Okay, but some of the downsides here. Okay, so some of the cons. Well, very inaccurate when we are far from the special point, and we have a straight line. Okay, we're using a straight line to approximate a curve, and that's bad, okay, because straight lines and curves are very different. So if you have a sine function like this and you try to approximate that with that straight line, it's really great near that point, but the farther away you get from that point, you have like the curve is down here and the straight line is all the way up here. So that's a pretty bad approximation the farther you get away from there. Okay, so an improved method is for us to use a polynomial. This must not be too surprising for you, to approximate a given function. And maybe some of the questions that may come up is, why do we bother dealing with a polynomial? Well, I'm going to sketch this out here. So let's just use our sine function here that we had going on before. And if you notice, it is possible for us to make a polynomial curve. So I'm going to call this sine function here f of x equals sine. And let's say I make a polynomial. Okay, so there are polynomials that do this. Okay, look at your Algebra 2 and pre-calc work. You can see that there are polynomials that curve like this. We can also make another polynomial that curves like this and comes back down. Okay, so the first question, I think, the first answer to this question, I should say, is because polynomials can curve. Okay, and that's something quite useful when you're trying to approximate these difficult curves. And not only can they curve as much or as little as we want them to. So the fundamental theorem of algebra says that we can arbitrarily, that, you know, however big the degree of a polynomial is, there is at least n minus 1 maximum that the polynomial may have. Okay, so however many times there are curves in this graph, we can generate a polynomial that curves that many times. Okay, so that's a really nice approach to this, or rather, at least in the big picture scheme of things, it's a good approach to this problem. Now, the details is where it's going to get tricky, and that's where we sort of have to pay the price for choosing this method. So with that in mind, let's look at Brooke-Taylor's idea. Okay, and he says, well, let's create a polynomial g of x that approximates some given function f of x. And the way to decide how often this is going to curve is that we are going to construct g so that it agrees with f at the special point. So construct g of x so that it agrees with f of x at the special point for as many derivative levels as possible. Now again, the special point is a place where we know the exact value of f, and derivative levels just means the first derivative, second derivative, third derivative. Okay. So in other words, this is saying we want to make g so that g of a, let's just say that the special point here is x equals a. So g of a is equal to f of a, g prime of a is equal to f prime of a, g double prime of a is equal to f double prime of a, and so on. Okay, so we want g to agree with f at point A for as many derivatives as we can possibly take for this function. And if all, and you know, Taylor's big idea was that if we can somehow get these two functions to agree for even for one point at a derivative, for a bunch of derivatives of it, then g will be a great approximator of f. Okay, so let's take a look at how this would work in our example. Okay, so it's going to take us several attempts, just like it probably took Brooke Taylor several attempts or more to figure out how this works. So remember that our example, let's just use our example here, f of x equals sine of x, and the special point was that x equals pi over 6. Okay, that was our example that we used in the last video. So first attempt. So let's call g of x equal to sine of pi over 6. Okay. Well, and then let's check the various levels. Check. What is g of pi over 6? Well, it's equal to sine of pi over 6, which is equal to 1/2. What is f of pi over 6? Well, that's also equal to sine of pi over 6, which is also equal to 1/2. Done. Great. Okay. First level, or the 0th derivative, is satisfied. Let's keep going. Let's take the first derivative. So this is 0th derivative. This is first derivative. What is g prime of x? Well, g of x is a constant. This is really just 1/2. So g prime of x is equal to 0. F prime of x, remember that f is sine, so f prime is cosine. And then f prime of pi over 6 must be cosine of pi over 6, which is equal to √3 over 2. And you can see here that these two numbers and these two numbers are not equal, so it failed. Okay, so this Taylor's idea failed here at the first derivative. So that didn't work too well. I'm going to end this video here, and then we're going to pick off in the next one where we try to make an improved guess at this value.